at the conclusion of this event, and so you can see the slides and the recording as well. At all times, please keep your telephone and microphone muted. This actually makes it easier. There's no background noise, etc., etc. In the event you do ask questions, please unmute yourself to do so. If you have actually dialed in using the telephone, please make sure you enter your audio PIN. As you may have noticed from previous webinars, if you don't enter your audio PIN, there's no way for me as the organizer to unmute you. Okay? Let's see. I think that's, and for those of you who prefer to ask questions by instant message, you can send me your questions by chat, and I'll relay them to Professor Dimakis. I guess with that, we're going to get started with today's presentation. We're delighted to have Professor Dimakis with us to talk about erasure codes and large-scale distributed storage. Dr. Alex Dimakis is an assistant professor at the Electrical and Computer Engineering Department, University of Texas at Austin. From 2009 until 2012, he was with the Viterbi School of Engineering at the University of Southern California. He received his PhD in 2008 and his master's degree in 2005 in Electrical and Engineering and Computer Sciences from UC Berkeley, and the diploma degree from National Technical University of Athens in 2003. During 2009, he was a CMI postdoctoral scholar at Caltech. He received an NSF Career Award in 2011, a Google Faculty Research Award in 2012, and an Eli Jury Dissertation Award in 2008. He's the recipient of several Best Paper Awards, including the Joint Information Theory and Communication Society Best Paper Award in 2012, and he's currently serving as an associate editor for IEEE Signal Processing Letters. His research interests include information theory, coding theory, signal processing, and networking, with a current focus on distributed storage, network coding, and distributed inference algorithms. As all of you know, storage is extremely hot today, especially with all the cloud-scale computing, and so we're delighted to have Professor Dimakis come and talk to us about that. With that, let me turn it over to Professor Dimakis.
Okay, so let me start. So this is joint work with my students, Mahesh, Megas, and Dimitris, and our collaborators from Facebook, Scott, Ram, and Dhruba. And I want to acknowledge our sponsors from the National Science Foundation for a Career Award, and also research gifts by Google and Microsoft Research. And I encourage everyone to ask questions if possible during the talk. It would be better, I think, to keep it interactive. Okay, so distributed storage systems, as is well known now, there is we're talking about clusters that have thousands or tens of thousands of machines, and it's very common, as we will see, to have multiple machines failing per day. And what I mean by failing, we need to get into more detail. It will be either a crash or a network failure or machine rebooting or being decommissioned or many kinds of different failures. But as the Google file system paper said, that we need to design with the failures being the norm rather than the exception. And for that reason, we must introduce redundancy in our data. So redundancy, the simplest form of redundancy is replication. Just keep many copies of your blocks. Here I'm going to argue that another form of redundancy that's information theoretic, that's called coding or erasure coding, is actually a much better way, especially as the amount of data stored is scaling. So here I want to show the default Hadoop architecture. So Apache Hadoop MapReduce has two components. The file system, that is called HDFS, the Hadoop Distributed File System, and the MapReduce infrastructure that runs on top. So this is the default configuration where you have, let's say, a cluster. Here I'm just showing 5 machines. And by the way, I assume that you can see my mouse pointer right now? Is that being
recorded? Yes, we can.
Okay, excellent. So here I'm showing just one machine that is a special machine called a name node in HDFS. That is sort of the machine responsible for the whole cluster. And then there is multiple other machines that are called data nodes or slave nodes that will be just storage slave machines. So here I'm storing 3 files. This is file 1, file 2, and file 3. And the first thing that HDFS does is it splits the files into blocks. And there's some fixed block size let's say the default is 64 MB, Facebook could use 256 or other numbers, but let's say it's 64 MB for now. So you take your files that you want to store in the file system, you cut them up in blocks like this, and here I will talk about the blue file, the green file, and the red file like this. And the first thing that the default HDFS will do is 3 replication of blocks. So every block, for example, the block 1 of the blue file is replicated 3 times like this. And then these blocks are being placed into the data nodes based on some block placement policy or a block placement algorithm. And there is a interesting research of what is the best way to place them, and there's many issues, load balancing, fault tolerance, etc. But I will not worry too much about it in this talk. Now the name node is a special machine that is responsible for keeping track of everything. It runs several daemons like a block fixer, that's an HDFS daemon that makes sure that all the files, for example, every file has a parameter that says these files blocks are 3 replicated. These files blocks can be 5 replicated, but the default is 3 for all files. Now the interesting thing that happens is that each data node could be storing blocks for multiple files, and we could be calling the collection of blocks from the blue file, for example, a stripe in this language. This will be more useful, of course, when we start talking about code. Now, at some point, there may be a failure, so data node 1, for example, becomes unavailable or crashes. And what's happening in practice is the name node is getting a pulse, making sure that all the data nodes are alive, and at some point, let's say it stops, receives messages from data node 1. So it will wait a little bit, and depending on the parameters, 5 minutes or 10 minutes, and then it will say, okay, this guy is dead, so I better start repairing all these blocks, because now you see I've lost block 4 from the red file, and I've lost block 1 from the blue file. And now I need to start a repair job. And when you exactly schedule the repair job depends on your workload and many other scheduling optimizations that are interesting and active research right now. But at some point there will be a repair job that will start that will say, okay, I need to make a new copy of block 4 from the red file and block 1 from the blue file. Now there are 2 selections that need to be done. Where will I place these new 2 blocks? And in my example here, I'm placing both in this new data node and in this data node 3 that had empty space. Or you don't have to place all of these blocks in the same machine. You could be spreading it out, and that would have several advantages. Now, the repair job when replication is happening is extremely simple. Is there a question? No? Okay. So the repair job is extremely simple. All you do is you've lost block 4, so this machine is currently unavailable. And after 10 minutes or so, you decide to issue a repair job. So now you're going to copy block 4 from an existing machine, and here I have conveniently placed a copy of the block 4 of the red file in data node 2 also, and I have also placed a copy of the blue file in data node 4. So that way there will be copies, these blocks will be transferred. The total amount of transfer in the network here will be 64 MB, which is the size of 1 block times 2. And these blocks will be read from data node 2 and data node 4. So that's the disk read I/O will be 128 MB, and the disk write will be 128 MB. So this is a...
Can I just jump in for one quick housekeeping item? There are folks who have joined in a little later. Folks, if you are trying to ask a question and you find yourself muted, if you've dialed in, you must have entered your audio PIN. Otherwise, all of you should be able to ask questions, or else send me chat questions for Professor Dimakis. And there is one individual who actually has got a lot of background noise, and if I unmute them, there's a lot of sound. So please send me your comments or questions via chat. Sorry for that, Alex. Please continue.
No problem. No problem. Okay, very good. So, okay, so let me know if there are any questions, and I will continue. So this is the very simple way that things are repaired in HDFS when there's block replication. Now, the next idea here is instead of replication, you could use erasure coding. Now the simplest form of Erasure coding is what I'm showing here. Here you have a file or data. Sometimes it's called a data object, so I will use file or data object interchangeably. And here we have split this into two blocks. So K in coding theory refers to the number of original blocks of your file. And with these K blocks, you use them to create N encoded blocks that have the same size as the original. And further, here, for example, it is just the new block is just the binary XOR of the bits of A and B. So that means if A is, this list of bits and B is this list of bits, A plus B, and I write plus because this is a bitwise XOR, but over what's called a Galois field, this is simply an addition operation bitwise. So you see here 0 plus 1 is 1, 1 plus 1 is 0, 0 plus 0 is 0, etc. So after I'm storing this XOR block, this XOR block has this very nice property that if I lose, let's say, block A, if I have B and I have this A XOR B block, I can reconstruct A from these two. Similarly, if I lose B, I can reconstruct B from A and A XOR B. So this A XOR B block acts as a wildcard, or it's called a parity, a single parity. And it can replace any one of the others as long as only one failure is present. And this is called a 3,2 maximum distance separable code. 2 is the number of original blocks, 3 is the number of total blocks created. And for example, this simple code is used in grade 5, and it's a very simple construction. Now things are going to get more interesting.
Alex, a quick question.
Yes.
I guess in A and B, I'm assuming that there's no particular size limit here. It could be few kilobytes to a few megabytes, I'm assuming.
So in the theory of error correcting codes, these can be yes, these can be arbitrary blocks. The importance is that the size of these blocks is always the same. So A cannot have a different size in bits than B, of course. In the way that these are used in distributed file systems like HDFS, these are very big. These are 64 megabytes. Each of these blocks is 64 MB. But the theory has no problem in an arbitrary size.
Okay. And the second question had to do with where is the Erasure code actually stored?
Okay. So there is a little bit of metadata that you need to keep track of the fact that this block is A, this block is B, and this block here is the bitwise XOR. So what you would be storing is there's a little bit of metadata that says what I'm storing here is A plus B, and then there is 64 MB worth of bits concatenated to that. So the information of where the code is stored is a small amount of information. For example, in HDFS, it's stored in the name node.
I see. So the name node has to have is sort of the golden node that has to be protected at all cost, basically.
Oh yes, yes, yes. So in the simple HDFS implementations, if there's a single name node, if you lose the name node, everything is gone. So for that reason, many implementations keep multiple copies of a name node, or there are several discussions about having distributed name nodes, and there are a few research papers and a few systems that implement distributed name nodes. But for now, we'll just stick to the simple name node that keeps track of everything. Okay?
Yes, thank you.
Okay, cool. So now the second question that one may ask now is, this is a single parity, which means we can tolerate a single failure. But now you may ask, how could I create a code that can tolerate two failures? So that would be a 4,2 code, because I start with 2 blocks and I have 4 blocks coded. And now I would like the property that any 2 out of these 4 allow me to recover the data. So now I'm going to try to draw on this thing. So here, for example, here I have A, and here I have B, and here I have the XOR, as we said. And here I have this strange thing that I call A plus 2B. Now what does A plus 2B mean? So what I'm doing is I can take the bits of A and I can group them in pairs of 2 like this. And now I can think of them as elements of a larger finite field. And for example, one simple way of understanding a field is as operation, normal arithmetic modulo a prime, so modulo 7, for example. And whatever will happen is that this will be a number, this number will be added to this number times 2. So 2 is another element of the field. So you multiply this number with 2, you get another number, you add it to this number, and because the field is finite, it will ensure that what you get here is another number from that set, and you're representing that with another binary sequence. Now, you can create finite fields for any size that is a power of a prime. You cannot create a finite field for any size you want, and there's a lot of theory about how you do these manipulations, but there's very simple implementations that one can use. Now, abstractly, the only thing you need to know to understand what this object is you can think of it as a linear equation that says a plus 2b. You can think of this as a real number. Let's say a plus 2b is, 15, and a plus b is, let's say you could read that this is 7. And now, if I give you these two things, you will have two linear equations that you can solve for a and b. And a and b, this is the example that shows if a and b were real numbers, but you can think of a and b being elements of a finite field. And now you can check that these 4 linear equations here are 4 linear equations of a finite field, and they have the nice property that if I give you any two, you will be able to reconstruct. For example, if I give you a and I give you a plus b, of course you can reconstruct b. If I give you b and I give you a plus 2b, you can reconstruct a, etc. So any two out of these 4 blocks will allow you to reconstruct your file. So this is a 2-parity erasure code, and it's a very simple system because it has really good fault tolerance, and it's used, for example, in RAID 6, etc. The specific way that you create these equations and you choose these coefficients so that this will work is dictated by what's called an erasure code. And the most standard erasure code is something that's called Reed-Solomon. That's the most widely used way of doing this. But there are many other ways that you could do this, including splitting in subblocks, etc. Very good. Now, my point here is that erasure codes are reliable. And by reliable, I mean more reliable than replication for the same amount of storage. Now, here I have a replication system where I took A and I made 2 copies of it like this. And here I took B and I made 2 copies of it. And here I'm comparing this system here, which is this replication system. I'm comparing it with our previous 4,2 maximum distance separable erasure code. This whole thing just means any 2 out of the 4 allow you to recover. Now, you can check, for example, here that in this replication system, if I lose this block and I lose this block, I have lost data, whereas here there's no single set of 2 that will make me lose data. So this system is more reliable than 2 replication, and they have the same storage. Now, in general, when you're storing with an n, k code, you can think of it as a black box that does basically the following thing for you. You take k packets, that's the input, and from these k packets you generate n packets. In our examples, k was 2 and n was 4. And these n packets that you produce have the same size as the original k, and you have this magical property that any k out of the n suffices to reconstruct the original file, so the original blocks. And it's easy to prove information theoretically that this property here is what's called the optimal reliability you would hope to get for that given level of redundancy. And it's well known, and that's why, for example, codes are used in many places, like Reed-Solomon, array codes, and DPCs and turbo codes are used in many applications, in storage, magnetic recording, distributed systems, wireless, etc. But the interesting thing in these problems that we're looking now, in these distributed storage problems, is that its packet now is stored at a different node distributed in a network, and that creates new complications. Now, as I said, the current HDFS default system would take, so let's say here that the block is 64 MB, so a block is this big, and this is 64 MB here. And what Hadoop will do by default is split this into blocks, and I chose 640 to make it 10 blocks. So this is the original file right here, and it's making 3 copies of every block. The problem, of course, with this is that this is a very large storage overhead, and this is very costly for big data applications. Now, Facebook engineers recently wrote an open source module that's called HDFS RAID. That is an extra component that is open source, and you can install it on your HDFS. What it does is it deletes all these blocks, the 2 replicas, and it produces these parity blocks instead. These parity blocks are stored actually in a different file in HDFS. It's called the parity file. And these parity blocks now are created using a 14,10 read Solomon. So K of the read Solomon that we had before was 10, and N is 14. So the 10 original blocks are, of course, the blocks 1 to up to 10, and these are the 4 extra parity blocks. Now, the good thing about this system here is that it can tolerate any 4 failures. So even if there are any 4 failures, for example, if I lose this block, this block, this block, and this block, even if I lose parities or systematic, so these blue blocks here are called systematic blocks, and these ones are called parity blocks, and if I lose any 4, I can still recover. The first parity here is the XOR, like the one we had before, and this one is a different linear combination, and this is a different linear combination, and the way these combinations are chosen is using this read Solomon algorithm that ensures that any set of 10 blocks here will give me 10 linear equations that are full rank and hence solvable over a finite field. Now, so my point here is that this the replication can tolerate 2 failures because, for example, if I have these 3 failures, I lose data. I've lost block 2. Whereas here, any 4, I will not lose data. Further, the storage cost of this system is 3x, whereas the storage cost of this system is 1.4x because I take 10 blocks and I produce 14. So it's less than half the storage. The second point I want to make here is that this saving of space has a scaling impact. So let's imagine that a cluster that's storing some amount of information. These are very realistic numbers. In fact, they're somewhat small for Facebook and Google scale problems. Let's say in 6 months period, your actual data doubled. So you had 6 petabytes and you went to 12. Now, if you're using 3 replication, the 3x will be changing the slope of what you're storing. So you'll be storing 30 petabytes. Whereas if you, instead of 3 replication, you switch most of your files into a 1.5 or 1.4x code, you would be storing half. So that allows you, a much better scaling behavior. And HDFS RAID, this system that uses read Solomon, has been deployed in Facebook analytics warehouses. And here I'm showing a plot. It's fairly old, but it shows already that this RAID module had saved up to 5 petabytes out of, this is the 30 petabyte cluster that I'm showing the benefits of here. So it's very significant benefits. And these benefits did not happen by RAIDing, as they call it, or encoding all the files. They only were encoding the cold files. So most of the files were still 3 replicated, but only a few of the files, the ones that were very rarely accessed, what's called cold, were actually read Solomon encoded. Now the problem with classical, yes?
Alex, quick question. Can you just repeat what you just said? They only encoded some files with the read Solomon codes, the others were all 3 replicated?
Yes. So in HDFS, when you put the file in, initially it will make 3 replicas of blocks. That's the default. Now there is a daemon that's running that has some rules that says, okay, if a specific file has not been accessed or has not been changed in the past, let's say 5 weeks or in the past 2 months, or you can set up some period, then what I'm going to do is I'm going to switch the replication factor of this file to 1. So HDFS will delete these replicated blocks. And then an additional daemon that's called a RAID node will create this new file here that's called a parity file. and this parity file will have just 4 blocks for every 10, and these 4 blocks for every 10 will be used in case of erasures. And this right now, when we started this project, only 8% of the Facebook warehouse was Reed-Solomon encoded. And I want to explain why. So the reason why the Reed-Solomon codes were not used more widely was the following problem. So I say Erasure codes are more reliable and they save space, but only 8% of Facebook data warehouse was Reed-Solomon encoded, and still that gave benefits. But the question is, why did it stay at 8%? The answer to this question is what's called the repair problem. So I will explain now what that means. But before that, I want to say our goal of my project and of this research is to create new erasure codes that will allow you to move to 40 or 50% coded data. So not only encode your super cold data, but maybe also some semi-cold data, that hasn't been accessed maybe in a week. It's not a good idea for most storage systems to encode all your data, because if you have some really hot files that many jobs are accessing, coding will delay the performance of these things, and you won't be saving much in space anyway, because most of the data, at least in the application I'm aware of, turns out to be somewhat cold data. So I want to explain why Reed-Solomon this is the main problem for Reed-Solomon, the repair problem. Now the repair problem is the following. So let's take the example, so are we clear up to here?
Yeah, Alex, there's a question that has come in on chat. It may be what you're just about to answer, but let me ask the question anyway. And yes. The question has to do with, is the penalty of Reed-Solomon simply more decoding time compared with 3x replication?
Decoding time it needs to be clarified. It's not CPU complexity is an issue, but that one is not the bottleneck in distributed storage system. The decoding communication and the decoding disk I/O are going to be the problems, which is, yeah, so the question that is asked is very central to what I would say. So let me explain exactly what I mean. So now we go into our example where you had these 10 blocks, and for these 10 blocks you produced 4 parity blocks. And now this is great. I say here we can actually tolerate n minus k, so n is 14 and k is 10, so we can tolerate 4 node failures here, and we will not lose any data. And most of the time, the first thing that happens is we have a single failure. So a machine failed, and the machine that was containing 3 was the one that failed. So I've lost this block. Of course, when I lose a machine, the data node, there are many other files from there are many other blocks from other files that are being lost, but let's just focus on this blue file for now. And every file is independent. Now, you lose this block 3 from this file. Now you need to repair it. How would you repair it? So you need to create in another position in your storage system another block that I will call 3'. And the reason I'm calling it 3' is because it may or may not be exactly the same as block 3. Now, here's the naive way you would do this. We know that any 10 out of those, so there are 13 blocks that are surviving, and they exist somewhere in our cluster. Out of those 13 blocks, any 10, by assumption, will give us back the original 10 blocks. So one thing I can do, and this is what's actually done, is I read 10 blocks from any 10 nodes, my favorite 10 out of these 13, and I send this data to this new guy. It's called a newcomer, and this new guy solves 10 linear equations, recovers the blocks 1 through 10, stores 3 in this new node, and throws away everything else. And that's how repair of Reed-Solomon codes is done now in all existing systems. Now this has, of course, many problems. It has the big problem that you need to move 10 blocks in your network for every 1 block that you lose. And further, you have disk I/O problems. You need to read 10 times more than the amount of information that you lost. So if you lose a machine that was 15 terabytes, you need to, and that was all Reed-Solomon code, you would need to read 15 terabytes times 10 from your cluster. Of course, this is happening in parallel, but still it is a very large disk I/O overhead. So the key question that if you're going to take something, if you're going to take something from this talk, the key question that you need to ask is this one. When I lose a single block in a coded storage system, do I need to reconstruct the whole file to repair just a single block? So here I'm just putting some numbers. I say what's called naive repair would require sending k blocks. And if the total file is size b, because each size of a block is b over k, then I would be sending, the total amount of information I would be reading and sending would be b. Now, here I want to say that this is a real problem and this is a big bottleneck, and that's the reason why most storage systems would limit the use of Reed-Solomon code. This is a plot from a Facebook cluster that it had approximately 3,000 nodes. Each node was around 15 terabytes of storage. This is an analytics cluster. And here I'm plotting the number of nodes failing. And for example, here you see that on a typical day you could have 20 up to 30 failures quite easily, and on a bad day you could go up to 100 nodes failing. And each node, remember, is 15 terabytes. So if you have 20 node failures, you've lost 300 terabytes worth of data. So the problem now is that if instead of replication you have Reed-Solomon encoding, you would be paying 10 times that in disk I/O and in repair traffic. So we calculated, for example, that for 8% Reed-Solomon, we get around 600 terabytes repair traffic per day, whereas the average network traffic of this cluster, which is not just repairing itself, it's actually running other jobs, was around 2 petabytes per day. And so basically 20 to 30% of the network traffic can be repair traffic. This is with very limited Reed-Solomon encoding. If instead you decided to go to 50% Reed-Solomon encoding, you would end up basically completely clogging your network. So this cluster would just barely try to stay alive, and its full network would be saturated with repair traffic. So this is the message that I want to say, that repair is clogging the network and the disk I/O actually, and this limits the Reed-Solomon usage. So our goal is to design new storage codes that have easier repair. And the first question that we asked information theoretically is if that is even possible to do. Because people believed that it is impossible to repair a failure without reconstructing the whole file. So that's sort of the repair problem. Is that clear?
Yes.
Okay. Now, the message I want to say is this one. Do I need to reconstruct a whole file to repair a single block failure? The answer is no. So that was the first thing we discovered in our information theoretic proof. Now I need to distinguish between two types of repair here. What is called function. So remember, I lost the block here. This is 3, but the dynamite is covering it. And the block I'm trying to reconstruct, I called it 3 prime. And now I'm saying 3 prime, the block you reconstruct, could be different than 3, but maybe you could still promise that any k out of n allow me to recover my data. So this is called functional repair. Functional repair means when I lose a block, I am creating a new parity instead of the block I lost, but I maintain the distance of the code, which means the any k out of n reliability. This property is useful because you don't lose in reliability, but it has the problem that before you had a systematic block, so you had data that was in the clear, but instead of data now 3 prime can be an XOR mixture of the or clean data with other blocks. So if you just wanted to read 3, it's not that easy anymore because you have to go and perform a decoding operation. So functional repair is not a practically very useful mode of repair, except in archival storage systems or systems where you don't read a lot. Exact repair is a more strict concept of repair that says the block I am reconstructing must be exactly equal to the block I lost. So for example, if I lost a systematic block, so clean data, I need to repair exactly that. And if I lost a parity block, an XOR, I will reconstruct exactly that XOR. So that's called exact repair. Now, The main theorem that we proved a few years back is that if you limit yourself to functional repair, the easiest of the two, instead of communicating the naive repair would be sending the whole file, and we assume the whole file is B bits. But now you could be sending this many bits instead. This is the amount of repair network traffic, also called repair bandwidth. And this function, so n is 14 and k is 10 in the examples, and you will see that it's tremendously smaller than communicating the whole file. And further, asymptotically, if you plug in, k and n different scalings, you will see that basically this scales like b over k, which is the amount of information that you lost, rather than the total amount of information in the file, which is b. So this was the first theorem that we were able to prove, but this was an existence proof that says there exist codes that allow you to do this, but we did not have explicit, simple codes that were usable. Further, we discovered a following interesting trade-off. We said that if each node stores alpha bits, this was before b over k, but now we're going to allow it to be a little bit larger, and repairs from d existing nodes and downloads d times beta bits, which is called gamma. There is a fundamental trade-off between the amount of storage per node and the amount of repair communication required. This is all for functional repair. And we characterize this information theoretic region that has this complicated formula, but it has a very simple shape. So this is showing that there's a trade-off between how much is stored in each data node and how much you need to communicate to repair. And there are two special points on this trade-off. There's this point here that corresponds to minimizing storage, so pushing this as much down as possible. And there is another point that corresponds to minimizing repair bandwidth that corresponds to pushing as much as possible in this direction. And this is called MBR, minimum bandwidth regenerating codes, and this point here is called MSR. Now the key point I want to say is that this is information theoretic bounds so that things much better than Reed-Solomon are possible. But we do not have explicit ways of constructing these codes for many choices of the parameters. So this was in 2010 when we published this paper, and then subsequently many people started researching the explicit and simple constructions of codes that satisfy this sort of capacity information theoretic result. However, from talking to the engineers in Microsoft and Facebook who work with distributed storage systems, they told us that exact repair is a key requirement for many of the storage systems they were considering, like cloud storage systems like Dropbox or data analytics that run MapReduce jobs. And they wanted exact repair because, for example, when they had the systematic block A and they lost it, they needed this new thing that was created to be exactly the systematic block A, the data in the clean, not some new parity, because that would mess up many of the read operations. So we had this theorem that said, okay, functionally, this is the amount of information that you need to communicate, but can you actually achieve this small amount of information if you require exact reconstruction or perfect reconstruction?
Alex, can you explain again? I missed a bit about why does Microsoft and Dropbox, etc., want exact repair?
Yes, because in their systems, the most common operation is the reading of a single block. So if the most common operation is the reading of a single block, if a job tries to read block A, for example, and because I had lost A, I have created now a new block called E that is a mixture of, let's say, E was A plus C. Now, I have not lost information. I promise to you that the fault tolerance of the total system is still any 2 out of the 4. But if you want to read A now, you have to read both this and now decode it. So you have to go and read C and move this around in the network and now XOR C with this. So you get A back. So this is a decoding operation that you need to do. So that's why yes, sorry?
No, I got it. Thank you.
Okay, yeah. So that's why you would want to have exact repair. Now, here in this example, I want to show that exact repair can be a tricky process, and here I'm just showing a very quick example. I will go over it a little quickly because I'm running out of time. But here I'm using subpacketization, so I've split a packet into 2 subblocks, and now I need to recreate them here. And if you do, if you say I'm going to send during the repair some linear combinations, I need to choose the coefficients of the linear combinations so that this newcomer receives 3 linear equations in 4 unknowns, but still is able to solve for the 2 desired unknowns. So this is a little bit of a technical issue, but I can get more on it later if there is time or in the questions. Now, the point I want to say is that many people have tried, and we are still trying to understand what is the exact repair region, and if this exact repair region can touch this blue bound. So we know that everything under this line is impossible, but we don't know if we can create exact repair matching this information theoretic line. So there has been a very large body of work in information coding theory by many authors that I've listed many of them here that try to push the boundary of this red region to match the blue region in as much as possible. And we don't know the fundamental bound, if this region could match. Now, what was recently proved is that this particular point can be matched, so there exists exact minimum bandwidth regenerating codes, and this point can be matched. There exists exact minimum storage regenerating codes. And very recently, in a paper that will appear in ISIT this year, it was proven that this intermediate region cannot be matched. So there were information theoretic bounds that said there is a gap between functional repair and exact repair. Now, the other issue is that the codes we have for this point are practical and they can be used, whereas the codes we have for this point, most of them are not really practical in the sense that the field size needs to be exponential and the files need to be enormous in order for this to be an actually implementable code. But we do know that it is fundamentally possible to match this point, but we still don't have very practical code constructions for this point. Now, in order to get to the practical side of this, we had to take a step back and said, okay, we don't know the full information theory of this, we're researching it, but we need to take a step back and create a system and see what is important in practice. So we basically decided to change the metric of interest. So the metric, as I said before, was the number of bits communicated for repair. And as I said, there's a lot of theory on this trade-off region. But instead of talking about this problem, we could talk instead about this IO, which is the number of bits read during repair. And this can or cannot be the bottleneck depending on the cluster and the application compared to the network. And this problem is open, so we don't know the fundamental information theoretic bounds, and we don't have codes that are optimal for this sort of metric. So this is metric number 2. And the metric number 3, which we do have some new results on, is just simply the number of nodes that are contacted during a repair. So these are called locally repairable codes. Sorry, not locally decodable, locally repairable. Okay. So LRC. So let me talk a little bit about this construction. So this is the code that we implemented in HDFS in our open source module that sits on HDFS. So you start with your 10 blocks. This is your original information. Then you can use a read Solomon exactly like HDFS RAID to create these 4 parity blocks, and these are called, we will call these now global parities. Global, and these global parities provide fault tolerance because they tell you that if you lose any 4 out of these 14, you will repair. And here we create this new block that is the bitwise XOR of only the first 5 of the blocks. So you take these first 5 blocks, XOR them together, and we call that X1. We call that a local parity. Similarly, we do this here, and similarly, we do this here. Now, these are called local XORs, and they allow single block recovery by transferring only 5 blocks. So, for example, let's say you lose this block. It's clear that you can read 1, 3, 4, 5, and x1, XOR these together, and you will reconstruct block 2. Of course, the problem with this is that your storage has gone up, because now you need to store these new extra blocks. So instead of 14, you're storing 17 blocks, so your storage overhead increases. Now, the next thing you can realize is that it doesn't matter that this is an XOR. You could choose any coefficients here and make a linear combination. So this local parity can be any linear combination of these four, as long as none of these coefficients is non-zero. And still, you would have the property that if you lose 2, for example, you can recover it by solving one linear equation that involves x1 and 1, 2, 3, 4, and 5, and 2 is unknown. So you can solve this one equation. Now the next idea that you can do here is that you can actually choose these coefficients and these coefficients. As I said, you can do anything you want as long as they're non-zero. So that if you take these local XORs and XOR them together, you could produce this block. Now this is a strange mathematical condition, but we prove that it can be done, for example, for read solid. And now this block no longer needs to be stored, because why was I storing this block in the first place? I was storing it to be able to repair parities, because if I lost P2, I could repair it by reading P1, P3, P4, and X3, XORing these together and recovering P2. So the locality, as we call it, of P2 would be 1, 2, 3, 4 blocks. So that would be the locality of this block, whereas the locality of this block would be 1, 2, 3, 4, 5 blocks. The locality is the number of other symbols you need to read to repair that symbol. And of course, you could also repair this, because you only need to read 5 blocks to repair it. So that's the locality of X2. Now, with this trick of what we call alignment, you can choose these coefficients and basically ensure that if you were to XOR the local parities, you would obtain this local parity of the parities. So you don't need to store this anymore. And now when you lose P2, what you do is you read P1, P3, P4, and then you also read this block and this block. And now you XOR these two blocks together, you obtain X3, and you XOR X3 with P1, P3, P4, and that's how you can reconstruct P2 if you lose it. And the locality would now become 5, because that's the total number of blocks you read. Now, this is the code we implemented in HDFS. And the HDFS system that deploys this code is called HDFS Zorbas, and it is an open source system. It's available on GitHub /navigator or from my webpage. And it has 1.6 storage overhead compared to the 1.4 of the HDFS RAID. This is the Reed Solomon construction here. So we store a little bit more in blocks. But we have this nice property that if we lose a single block, we can now repair it by reading only 5, whereas Reed Solomon would require reading 10. So we implemented this full system. This is just an example of the encode function. It's all written in Java. And we ran several experiments on an Amazon cluster and on a Facebook cluster. So here, for example, in this example, the total number of nodes that we had was, let me see, so this was, so 37 nodes were live at this point. So we went up to 100 nodes. That was the size of the cluster we had. So the 50 machines of the 100 were running HDFS RAID. This is the Facebook version that deploys the 14,10 Reed Solomon code. Whereas 50 were running our version of this system that is called HDFS Zorbas. It had this complicated code name before. 50 files were uploaded, for example, on this system. This is just choices we did for one of the experiments. And we were killing nodes, and we were measuring network traffic, disk I/O, CPU, etc. during these node repairs. So here is a measurement of the system. Here you see this is actual physical time on this axis, and at this time there was a failure happened. So this is the network traffic that the Reed Solomon system is performing, and this is the Zorbas R system, the one that uses this LRC code, locally repairable code. And you see that it is, as expected, it is communicating half the network, And further, more interestingly, there's a little bit of a gap here. You see, especially that gets bigger as the number of failures is increasing. That says that the repair process, the repair job, is finishing faster. So this first failure event involved killing one node, again killing one node, 2 nodes, 3 nodes, etc. So this is different failure events. And these ones involve more nodes, and we killed more blocks. This is the same. Okay, here we have also the information of how many nodes. This is how many nodes were killed, and this is how many blocks were lost when we killed that one node. So here we killed one node which contains 62 blocks. Here we killed one node which contains 71 blocks, etc. And here what I'm plotting is not the network, but rather the disk I/O. So I'm plotting the bytes read by the file system during the repair job. And you can see that the Reed Solomon has more than double the disk I/O compared to our LRC construction. So our LRC construction is red. Here, these were the most severe of the failure events, where we killed 3 nodes in 2 cases, and we lost around 200 blocks in each. The CPU plot is just here to show that the CPU is not really a bottleneck in the system, and it was approximately the same. The HDFS CPU there was many other jobs and daemons running in the back, and the decoding was not an issue. Here I'm showing the repair duration in minutes. So you see Reed Solomon, for example, would repair a failure in I don't know, 25 minutes, whereas Zorbas was repairing less than 20 here. This is in general true. You see there's a gap in the repair duration time for these events. So Zorbas also repairs faster, and this is of course expected because it's moving less in the network and it is reading less bits from the disks. This is another experiment where we were running a MapReduce job in parallel to and seeing how there are missing blocks and how much the missing blocks delay the completion time of another MapReduce job. So the gray plot is the duration time of this word count job. So it's 10 word count jobs. This is the duration if there were no blocks missing, so that's no failures. And now if there were 20% missing but we used the Zorbas system, this was the time, the extra time, whereas in the Reed Solomon this was the extra time. And you can see it's more than double the delay, the extra delay that Reed Solomon required compared to the Zorbas system. So this is just a summary. The new storage code, the LRC reduces the bytes read by roughly 2.6x. The network bandwidth is reduced by approximately half. We need to use more storage because we have these local parities that we're storing, but the CPU use is very similar. In several cases, we also saw that the repairs were happening faster, and our ongoing study is showing that the bigger the system, this gap is increasing. And we provide 4 more zeros of data availability more compared to replication. And there's a number of reasons of that because we have more fault tolerance, and also compared to Reed Solomon, we repair faster. So the gains can be much more significant if larger codes are used. For example, for archival storage, one could use a block size not of 10 but rather of 100, and then you could have very high data rates and very high availability. So conclusions and open problems. As I said, there are many theoretical open problems in this area that's called coding for distributed storage. I said the exact repair region information theoretically is still an open problem, and many of us are working very hard to characterize it. Further, if you limit the field sizes that are used, in practice the field sizes needs to be 2 to the 8 or 2 to the 16, but they cannot be some super exponential numbers. So creating codes that have small finite fields is a very important practical problem. Further, sometimes there can be bit errors, either because there are hardware problems on the disks that produce errors, or because there's malicious nodes potentially in a peer-to-peer storage system. So these codes can protect or provide privacy in several of these scenarios, these distributed storage codes. So there are interesting open problems there. Another area that is important is the topology, designing the code, keeping in mind that the topology is not completely flat, and the communication between some nodes can be much cheaper compared to the communication between other nodes. For example, if the nodes are in the same rack, or across racks, or even across data centers in a geo-distributed system. So there has been some very recent work on this, and this is a very interesting area. There are also, as I said, the amount of information that needs to be read is completely open. The number of nodes that need to be communicating during repair, there has been very interesting recent work on this, and we understand this locality better. These are the codes that have been implemented in HDFS by us and in the Windows Azure storage system by Cheng et al. In this very recent paper that is deploying local codes in production. So I say there's significant potential for use in real systems. In fact, some of the new systems are using them, like the Azure system, and the benefits can be tremendous. They can be in tens or hundreds of petabytes of savings, depending on the size of the cluster. I want to say as a final comment that depending on the use of the storage system, different codes need to be designed. So, for example, if it's a data analytics cluster, it's a different problem. If it's a Facebook haystack type of a system that stores photos, the use is different. Or if it's a system that uses solid state drives, also, the code could exploit several structural properties of the workload. So it's not one code that's going to be perfect for all the design, for all the problems, but rather many. So we're working on a few different codes for archival storage, for example, or for across data center problems that require communication across data centers. So, and also finally, I'll just say I maintain a wiki, the distributed storage wiki, that it's linked from my homepage. And here I try to summarize the bibliography. There's hundreds of papers on this in this area, and we try to. It's a wiki that many people are contributing. There's a bibliography that's updated online, and we try to maintain the state of the art and know what is happening in this area. So this is the end of my talk.
Alex?
Yes?
Are you done, or are we opening it up for questions, or where are we?
I have, yes, I can take questions. I have approximately 15 minutes.
Okay. Okay, so folks, first of all, thanks, Alex, for a great presentation. Just one bookkeeping item for folks that need to leave because it's 1 o'clock here Pacific time. Our next seminar is actually going to be on June 7th, and the topic there is an interesting one on predicting communication intention in social networks. So if you feel that that's up your alley, please click on the link on our website and join that. In the meantime, I guess, folks, if you have any questions for Professor Dimakis, please, ask them now. And thanks, Alex, for a great presentation. Any questions for those who are unable to unmute themselves? Please send it to me via chat. But others who are all unmuted, please feel free to ask your questions. So Alex, let me ask you one question while maybe people are thinking about what they need to ask. In terms of the problems that you said are open problems, on your last or your second to last slide, the rack aware, location of the data center, or even data center aware. The reason for that building in that awareness is simply to minimize bandwidth, I'm assuming.
Yes, because the point here is that if you have machines that are, some machines are grouped in clusters, as is happening, in racks, as is happening in most clusters, the communication inside the rack is much cheaper than the communication across racks, and can also be much faster. So the cost should not be the total repair bandwidth that measures the total amount of bits that are being transferred, but rather the number of bits that are being transferred locally should be costing a different measure of cost compared to bits that are transferred from further away in the data center. And this can become even more a 3-layer or multi-layer hierarchy, where if you're running a distributed storage system across multiple data centers, which is a very interesting problem, then sometimes you don't want to be replicating your data centers fully, so you could be creating codes that have some blocks locally, and they can handle a number of failures, a small number of failures locally, but even if there are bigger failure events that would be more rare, they can still be repaired by transferring across data centers. But of course, the transfer across data centers has to be counted much more as a cost or as a delay. So one way that you can merge them is by looking at availability from the mean time data loss, and then you can put in explicitly the transfer rates that are happening, and you can try to make it one objective that way. And there has been some work on this. I'm not sure exactly how different applications will require different costs. I think right now for clusters, the main cost is, I think, the disk I/O. So that's why we focused more on local codes, which minimize the number of nodes that are being involved in a repair process. But I think as the systems are getting bigger, maybe the network might be more important. Theoretically, none of these problems is fully understood. But practically right now, the construction that we worked on was minimizing the locality. I mean, of course, it had very good repair bandwidth also, but it wasn't optimal.
Okay, thanks. There's one question that has come in via chat, and let me just repeat that. The question is, so the topology optimization problem can translate directly to a block placement problem?
Very good question. So the block place, it's not exactly the same problem, but block placement matters a lot. So if I give you a specific storage code, like for example, let's look at this code. That's a good question. So let's look at this code here. Let me see now. Okay, so I can get to my pointer. Okay. Now imagine that these blocks 1, 2, 3, 4, 5 are placed in different racks. Sorry, let's imagine that all these are placed in the same rack. So this is rack 1. Now, if I lose block 2 and I try to recreate it in another machine that is placed in rack 1, then all this information will need to be transferred inside rack 1. So that is a good thing. However, this code design, for example, allows, by the way, notice here that there are some sets of 2 failures. For example, this set of 2 failures, the failure of node 2 and the failure of node 6. This is a set of 2 failures that both failures can be repaired with local repairs only. So for this repair you can use X1, and for this repair you can use X2. But in this code, let me go back, there I am. There are other sets of 2 failures that cannot be repaired with local parities only. For example, if I lose this block and this block, so now I've lost 2 blocks from the same local group, as we call it. Now this local parity alone cannot be used to repair this failure. So one way, for example, to repair this failure now is to read 10 blocks. But that would, for example, read 1, 4, so you could read 1, 4, 5, 6, 7, 8, 9, 10, and these 2 parities. And now you bring all these blocks in a new machine, you recreate everything, you recreate 2 and 3, and that's how, and you write them. So now that would require communication across racks. So there is a certain sets of 2 failures that can be repaired locally, and certain sets of 2 failures that require this global parity. Now, in general, how you place things in racks is a very good question, and optimizing the placement is actually not fully understood, in my opinion, to maximize the reliability. but the placement of blocks and the problem of designing the code should be coupled, I think. If you do this jointly, then you can get better performance than somebody giving you an arbitrary code and now you try to find the best placement for that code. But I don't think that we have a full understanding of these problems now for what's the optimal placement. But it's definitely a very interesting question.
Any further questions for Professor Dimakis? Okay, I guess if there are none, thank you so much, Alex, for a great presentation. Folks, you have Professor Dimakis' wiki page. You have his contact information. If you need to reach him directly, you can contact him or contact me for those of you that want to connect and have follow-up questions, etc. But continuing our usual tradition, please unmute your phones and let's give Professor Dimakis a warm round of applause and a sort of a virtual thank you here.
Thank you.